Hello class, this is Ms. Riggins with today's video on section 5.4 in logarithmic scales. As you're watching the video, please write down important notes, formulas, or statements. Feel free to pause, rewind, or even replay the video as often as you need. And don't forget to submit your WISC summary as well as your top question. Today I'm filming from a different location, and I wonder if you guys know where that location may be. I'll give you a hint. Look back here at this big flag over here. It's not in Texas, but still close to it. So let's begin with today's video. Here, if you guys remember from astronomy, the distance from the sun, that all the planets in the solar system are, my very educated mother just served us 9 pizza pies, Mercury, Venus, Earth, Mars, Jupiter, and Uranus. If I were to look at the distance from the sun between each of these, as you know, Mercury is closest, so the distance is the smallest, and Pluto is the farthest, and as you can see, the distance is the largest. And if I were to add other galaxies as well, the distance from our sun would be very, very large. Well, if I were to graph these distances on a linear scale, in other words, the intervals are evenly spaced, as you can see here, I can only really fit the first 5 planets on a scale from 0 to 1,000 in millions of kilometers. And if I wanted to fit all 9 planets, I can make the scale larger instead of every 100 years, making it from every 100 million years, every billion years. And even that being the case, I would have an issue because, as you can see, Mercury, Venus, Earth, and Mars are very close together. They're within 1 billion kilometers from the sun, while the others are pretty spaced apart. So the linear scale really isn't helping us be able to fit all of our data points on the same graph. So we may need to look at a different type of scale, and that scale is a scale that's not evenly spaced, because we have this problem with evenly spaced intervals, but it's a logarithmic scale where the spaces are not evenly spaced, but the exponents are evenly spaced. As you can see here, 10 to the 1, 10 to the 2, 3, 4, 5, 6, 7, 8, 9, 10 as well. But the values and the orders of magnitude are evenly spaced, but the values aren't evenly spaced. And as you can see here, we do have some flexibility, and we are able to fit a lot of our data points where they're not so smushed together. And then we can even fit on here the Proxima Centauri, as well as another galaxy, the Andromeda galaxy, all in the same one, because we graph these data points on a logarithmic scale instead of a linear scale. And the logarithmic scale occurs when the graphs are when the values of the data points are too different. They vary too greatly in size, not just in values, but in size. Let's take a look at another example of when we would need a logarithmic scale. Let's take a look instead of distance in time, in the years that on this planet. Okay, so as we can see here, we have this table that tells us of certain events that occurred throughout time, and as we can see here, those values greatly vary from 1 all the way to 4,450. But if we take the log of each of these values, then we've kind of smushed or scaled them so that they can fit in more reasonable scale. So as we can see here, man emerges is 10 to the 0, which is 1. Then around 10 to the 70, we get the 8 man, and vice versa. So in this case, we have a logarithmic that's based off showing the various ages on a logarithmic scale in millions of years ago. And so they're more evenly spaced, and if we had to start from 1 all the way to 4,450 million years. Here's another logarithmic scale, but instead of doing it to the 0.7 or 10 to the 1.5.7, we do it evenly spaced intervals with 10 to the negative 4. And evenly spaced, not intervals, but evenly spaced exponents, as you can see here. And again, we're able to fit a lot of different things, but we kind of switched it. If you notice, why is it the demise of the dinosaurs and things of that sort is over here at 10 to the 2, whereas over here was at around 10 to the 1.83. So it seems like the scales are switched, and the reason being is because that if the events are less than 1 million years old, then they're indicated by negative exponents. So we still are graphing these based off a logarithmic scale, but a little bit different is that in this case, 10 to the 0 is really the midpoint of when we start, but in our graph it's the middle point. All right, let's take a look at another example of another scale using, in this case, compare it with the axes labeled with actual values, not logs. And as you can see here, they're very spaced apart and smushed and things of that sort. Okay, so why is this of any importance and value? Well, one more thing, we want to talk about log-log scales, where not only are the y values very different in size, but so do the x values. And as we have here, if we were to graph weight versus rate of metabolic rate, I have a problem saying that word, the weight varies greatly, and so does the rates vary greatly. So we would have to take the log of each so that we could have a good explanation, a good way to describe them all where they fit nice and pretty on one square grid. Whereas if they weren't in logs, then we would have a hard time finding a square grid that we could graph them in. So why do we do this? What's the importance of graphing in logs? Really, the basic thing is to be able to describe or to just graph the data in a nice and pretty way and format. Another option, and we're not going to go in depth about there, is if I have exponential data and I want to linearize this, which is look at the graph, the data in a linear way, even though the data is not linear, we can do this using logs. How? Well, here we have some exponential data. As you can see, when I plot the data, it's an exponential decay function. But I can take the log of the LPs. So log of 244 ends up being 5.5. And then when I graph the CDs versus the log of the LPs, I get a linear type regression line, as we can see. Not that the data is linear, but the log of the data is linear. That's for people who like to see it in a linear sense. So how do we do that? How do we fit an exponential function to data? Well, we take the log of both sides. So here we have an exponential function. We take the log of both sides, and we take the log of both sides. We end up with the natural log of a, the starting value, plus k to the t. If we had this exponential, this natural exponential form. Well, this looks very much like a linear function because natural log of a is a constant, k is a constant, and t is the value that's changing. And we can use linear regression on the variables t and y to come up with a linear function that fits the data. And then if we want to transform our function back into the original values, we can do that by substituting natural log in for y and solving for n. Alright, so that's the basics of the video. We're actually not going to have any, I'm not going to demo any sample problems on the video because we're going to do that in class, and we're not going to have a VA or a skills test on this topic. It's just something good to know for those of you who are going to be going into applied fields where they use logarithms in this. Okay, that's it.